All right. Hey, everyone. Welcome to DSUA-111, Data Science for Everyone, Jeff's section for April, what would be April 17th, but I'm recording this on April 16th. And today we're talking about confidence intervals, even though really I want to get you to regression, since there's one question on the project which asks you to interpret a confidence interval, whereas there's 4 questions that ask you to run a regression analysis from scratch on your data set and interpret it. So I'm going to do the lab in lab 8 in this video, but then I'm going to record another video showing you just how to do a basic regression so that you can go to the next step in your project, regardless of where we are in lecture. So this is the lab 8 video, but stay tuned for the regression video. For now, let me share my screen. So yeah, we go to our DSUA-111.rcnyu.org. You click spawn server if this is your first time logging in for the day. Otherwise, it shows up. Click assignments tab, see lab 8, click fetch, and then we can, sometimes I go back to the files tab and I get it, or we can just go right to the downloaded assignments section right here, expand the arrow and click lab 8, either way. So yeah, we are looking at a data set about, well, we're looking at a problem that involves a data set about piano tuners. Piano tuners, if you don't know, they're people who come to your house and they tune your piano. And yeah, we're gonna compute test statistics, we're gonna do bootstrap, or we're gonna do confidence intervals based on this data set. So what's the word? The idea here is that, yeah, sometimes we're trying to estimate unknown quantities about a population, right? That's, in fact, pretty much what you're doing in almost all data science projects. So for example, if you are in your project, if you're looking at the effect of GDP on, if you're looking at the effect of GDP on COVID infection rates, really the unknown quantity that you're trying to estimate is for a given increase in GDP, how much does that change likelihood of getting COVID or something? So pretty much any data science project you do can be phrased in terms of estimating unknown quantities. So if we can't count the population, right, then actually the size of the population is an unknown quantity. And so we need to make guesses based on samples. So far, you've been making guesses based on samples for the mean of a population. That's the standard thing you do in a data science class, is you say, oh, I don't know the population mean, but I have this sample, and what can I say about the population mean from the sample? But mean, right, the population mean is only one of the many, infinitely many things that you could try to infer about the population from a sample. So in this case, we want to estimate not the mean, but actually the total number of piano tuners that work in New York City, right? So say they're in a piano tuners union or guild that assigns them a number, right, from 1 to n. So each piano tuner in New York City has a unique number starting from 1, counting up until every tuner has a number where the final tuner gets the number n, which is the total number, right? So if there's 500 tuners, then each of them has a number 1, 2, 3, 4, and so on up to 500. And here, the unknown quantity is n, right? And so one first stab at it, this is called a back of the envelope calculation, which is where you just kind of you make estimates about parameters about the world and use it to infer things. So in this case, we would use how many people live in New York City, how many people of those 8 million that live in New York City have a piano, blah, blah, blah. And this is actually something you'll, like if you want to go into computer science or data science, you'll actually be asked to do it a ton. Like in my Google, I think it was like a Google interview, they asked me, this was like, I'm old, and so this is when Netflix like physically sent you DVDs in the mail instead of being like a streaming service. And they asked me like, oh, do a back of the envelope calculation, kind of like this one right here, of how big would a warehouse need to be to hold all the DVDs for Netflix. And so they wanted me to do things like, say like, okay, well, how many movies does Netflix have in total? And then be like, well, you know, let's say first, the simple case, let's say they just have like 5 of every movie. How much space would that take up? So then you have to like calculate the space of a single movie and then multiply by, you know, 1 million, however many movies there are. And then like later in the interview, you know, they want you to like keep expanding, keep making it better. So I was like, oh, but maybe they want like 100 copies of super popular movies and then 1 copy of not popular movies. So how does that change the distribution or number of movies they have? But the point is like this type of thing is good to know if you're a data scientist. So feel free to read this in the article that's linked. But they estimate like 200 piano tuners, right? But we are statisticians, right? Or we're data scientists. So we want to take a more like less hand-wavy, a more statistically principled approach, right? So what we'll try to do is generate like mathematical or like quantitative evidence for some guesses against others. So we get to question 1, which is, you know, what we've been doing in this class so far is like, we can sample from a population a bunch of times, and for each sample we can generate an estimate, right? But sometimes like you don't have enough data to just keep sampling from the population, right? Like if you just spent $1 million to do a survey, it's not that easy to just go out and do another $1 million survey and another $1 million survey a bunch of times. But instead, we can do what we've been learning in the past week or so, which is like resampling from the sample. So we've learned like bootstrap method, we've learned permutation tests, we've learned different ways to like treat our big sample as kind of like, all right, this is all the data we have, and then do fancy statistical methods to kind of squeeze as much information as we can out of those samples, out of that one sample that we have. So here, we know that the piano tuners are labeled 1 to n, right? And n is the largest label. So imagine we have a sample of tuners, right? That single sample with their labels. So in our sample, we only see a small number of labels. We can also assume that the sample came at random from the population. So yeah, we went out and did like a good, you know, well carried out random process to sample people in New York and like ask them if they're a piano tuner, and if so, then like what their number is, and we recorded it all in a big data set. So now, if we do that, is n a parameter or a statistic? So remember, this time we've been talking about n is the label, like the largest label that any piano tuner in New York has, right? So the important thing to think about here is that that person, right, say piano tuner n, they might not be in our sample, right? Meaning the largest n, so the largest piano tuner label that we see might not be the largest one in the whole population. In fact, like, it's not likely that it is, right? Like if you labeled every person in the US with a label like 1 to 340 million, like what's the probability that if you sample like 100 people out in the US, that you'll actually find like the person labeled 340 million? It's pretty low, right? So the point of me saying all this is that parameters, right? A parameter is a property of a population, right? So the actual like highest numbered piano tuner out in the population of New York City, that's a parameter, whereas a statistic is something that we've derived from our sample, right? So two important terms, because like the whole point of what we're doing in this class is to take like compute statistics, which we can do because we have samples, and try to infer things about the parameters, right? We almost never know the true value of the parameter. We're trying to come up with estimates of the parameter that are as good as possible. But n itself, in this case, is a parameter, right? Because n, just capital N by itself means like the highest label in the entire population, right? And so that we'll never know from a sample. We are just estimating from our sample. So it's a parameter, right? It's a property of the population, not our statistic, because we have no guarantee whatsoever that our sample will contain the largest label, n. Cool. But now, getting more to what we're going to do, we use our random sample to compute a number n hat. That's how you pronounce this in math world, because it's like it's wearing a little hat, right? Hat like that. So n hat, right? So we compute a number n hat that estimates n using the sample, right? So now, is n hat a parameter or a statistic? It's kind of a leading question, because now it's saying, okay, now we are taking into account that we can't know the true n from the population. So we're making this n hat as like an estimate, right? And that estimate, we can compute that from the data we have in our sample. It's kind of helpful because in general, like in data science and math and stats, hat almost always means estimate, right? So if you have some parameter like alpha, they're trying to estimate about the population, and you see alpha hat, like these conventions are helpful because you don't have to ask the person like, oh, what is this alpha hat that you wrote? You know, oh, hat means it's an estimate of the population parameter. So in this case, n hat is a statistic, right? N hat is something we compute from our sample. So the answer is B, because it's something we compute from our sample, even though like the aim is to estimate something from the population, capital N without a hat, but we'll never know capital N without a hat. So n hat is kind of like, we're going to do the best that we can with our sample data. Cool. And so part 1C says, all right, now we actually have data from a file, so piano_tuners.csv, right? So this, if you run it, this code is provided to you. If you run it, this is the starter code that you've seen before, where the key thing is that it reads a CSV file, right? PD means we're using the pandas library, and read CSV means we're using its CSV loading function. And CSV fpath is just something that it computes. Like long story short, figuring out where this pianotuners.csv is gonna live on your computer, and then also where it's gonna live when we auto-grade it, right? So the tilde, I mentioned this in section like many weeks ago, but that's just saying, this character right here, tilde, is saying like, go to the home directory of whatever user is running this code, right? So in this case, when you're running it, it will go to like, you know, your net ID as the home directory, whereas when the auto-grade is running it, it will go to like instructor/shared/piano. And it's just to make sure that it goes to the correct place on the disk. Cool. Like the correctly named folder path. Okay, and so we have observations, and also know that it like we write down kind of like right after we load it, we write down or we record how many observations there are in this number of observations variable, where it's just we call len, right? That's a Python built-in function that finds the length of whatever you give it. So in this case, the length of observations is the number of data points we have in our data frame that we just loaded. And then, since it's the last line of code in the cell, we just put observations there, and it shows us what's inside of it, right? So what we see is that observations is a data frame, but it's kind of weird because it only has one column, right, called label, and it only has 17 rows, right? Careful, because it's counting from 0, so it's 0, 1, 2, 3, 4, ... up to 16, right? So you have 1 through 16, but you also have zeros. That makes it 17 rows total, and it says that down here in one column. Cool. So note that we have 17 observations, and the maximum value in the label column is 135. You can't actually see 135 here, but you could compute that really quickly by just saying like observations dot max, right? And we would get 135 is the maximum of label. We could do observations, take out the label variable, and do max on that, and then it would just give us the number. So this whole time, when we've kind of been sweeping under the rug that there's all these different ways where you could take like a statistic, right, something computed from your sample, and use it to infer something about your population, right? We've just kind of said like, okay, we'll make a thing called the sample mean, right? We'll take the average of all the things in our sample, and then we've kind of just almost like implicitly just said, okay, well, that's now our estimate for the mean of the population, right? It's like this lab is helpful, right? Because we're not trying to estimate the mean of the population anymore. We're trying to estimate the size of the population, right? So it makes it really explicit that like there's all these different ways that we can use to try and estimate something about our population. So in this case, we're going to define two different ways of estimating the maximum, right? So like what the biggest label is in the population from the labels in our sample, right? So the first way, so question 1C is it gives you the start of this function called max-based estimator. So it inputs an array of numbers and it outputs the maximum value, right? So this is one way that we can estimate the sample size, which is just take a sample that we're given, find what the highest number in it is, and just guess that as the population one, right? It won't be exact unless we actually get the highest labeled person, but you know, it could be close. Like if there's 300 total and we happen to include number 298 in our sample, and that's the highest one, that'll be pretty close, right? It'll be off by 2. So this is like an okay estimator if you're lucky. If you're unlucky, like you just get, you know, there's 500 tuners, but you only get tuners between numbers like 30 and 50 in your sample, and then you guess like 50 because that's the max of your sample, but that's way off the actual population max of 500. But point is, we're going to just use the np.max function. We're going to call it on array of numbers, and we're going to return that, right? So it just np is numpy. I didn't like make this up. It says you may find the np.max function up here. So np means I want to call a function from the numpy library, and max is what you'd expect. It just finds the biggest number in a list, right? And so now we have a function that's ready to be used for like computing test statistics that just takes the max. So cool, and we can like test it, right? We could just write code underneath this, what we call max-based estimator on like, you know, 5, 10, 15, 20, and it will give us 20, right? Whereas if we added an element to the beginning, like 50, so now it's 50 is the highest thing in it, it should give us 50, right? Cool. But now here's another way that actually, like, it's not an intuitive way to try and estimate, you know, the size of the population, but it turns out it actually works better in a mathematical way, which is if you think about like the average of any numbers from 1 to n, you might have learned this in like pre-calculus or some class like that, some like high school math class, that if you take all the numbers between 1 and n, and you average them, the result is always n, right, which is the largest. Like, so if you're computing the average of numbers between 1 and 20, n is 20. So 20 plus 1 divided by 2. So 21 divided by 2 is the average of the numbers between 1 and 20, right? So if you think about it, we can take the average of like a bunch of numbers. So let me write this out in LaTeX a little bit, just because. Here, I'm going to copy this. I think this could be helpful because there's a lot of parts skipped there. So let me make this markdown. All right, so here. that to us. Nope. All right, so what we have is like the average of all the numbers from 1 to n. Sorry, I should say like 1 plus 2 plus c dots plus n. Okay. Doesn't like that. There we go. I'll just do that. So the average of 1 plus 2 plus dot 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 plus n, right? The point is the average of the numbers between 1 and n. So I'll just do 1, 2, n. There. The average is like you add them up, right? So that's this part right here. 1 plus 2 plus dot 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 plus n minus 1. So the second to last number and then n. And then when you take an average, you divide by the number of numbers that you have, right? That you averaged over. So in this case, that's n, right? When you do that, like I think it was Euclid or Euler or some mathematician like that. No, it was Gauss. Gauss figured out that the average of all the numbers from 1 to n is always n plus 1 divided by 2, right? So if we want to get an estimate for n, we can do some like manipulation of this formula, right? And what we can get that's equivalent, just using like algebra, is that 2 times the average from 1 to n is n plus 1. I should say like implies. Cool, right? So if we just like take this 2 in the denominator here and we multiply it back over here to our average, we get 2 times the average is n plus 1, right? Which means that, right, so which implies that n is approximately 2 times the average. Right, so approximately, it's going to be off by 1 on average, but that's fine. If we have really high numbers, being off by 1 doesn't matter. Like we're happy if we estimate 499 and the actual total is 500, right? Or if we guess 501, but the average is actually, the number is actually 500. So our estimate, right, for n, and we can always get an estimator for n, which is what we're looking for, by taking the average of the numbers from 1 to n and multiplying it by 2, right? So in this case, we can take the average of the numbers in our sample, right? It's unbalanced, like that. So we can take the numbers in our sample, right? We can take the average of the numbers in our sample. Like this would be average from 1 to n would be if everyone was in our sample. But in general, we're going to have like a random sample. So it's just going to be numbers, some spread of numbers between 1 and n, right? So we'll just hope that, our sample is big enough that it's close to the average, right? Meaning the average of our sample is close to the full average. And then we use that average to get an estimate. So, sorry, I should say hat. And hat, right? Our estimate for n is going to be 2 times our estimated average. So all right, I'm literally just going to sample average. Oh, I see. Finally. So we get an estimate for n by taking our sample average, right, and multiplying it by 2. That's all I'm saying. Is that now, instead of np.max, which we used up here, we use np.mean of the array of numbers, but we will multiply it by 2, right? So return 2 times the mean. Cool, and we can test that one by saying like, okay, mean-based estimator of 1, 2, 3, 4 is array of numbers. I wrote array of number. Cool. So the mean-based estimator of 1, 2, 3, 4 is 5 because it takes the average of these 4 numbers, which is 2.5 and it multiplies it by 2, so it gets 5. So it's pretty good. And like if we, if we made the array bigger, again, it's just going to be off by 1, like our formula said. But so since it's a sample, say like, oh, we sample everyone except like 7's gone and 2 is gone, it's still pretty good, right? It says 11.5 and the amount was 10. Now let's say 10, right? The actual n isn't in our sample. We actually get even closer. We get something that rounds to 10, which is the actual n that we wanted to estimate, right? So the point is like, from this sample of the numbers between 1 and 10, we take the mean and we multiply it by 2 and get a pretty good estimate. Cool. So these are our two ways of taking a sample that we have and guessing a population parameter. We can either just say, okay, it's the thing we usually do with the average, where it's like, okay, I'm just going to guess that the average of my sample is the same as the average of the population, or at least as close to the average of my population. So like if someone says, oh, what's the average of the population? My answer is going to be, take a sample, find the average of that, and tell that to them. Whereas in this case, we have two different ways of guessing the number of piano tuners, right? One is someone says, what's the number of piano tuners? We quickly take a sample and we just tell them the highest piano tuner number that is in our sample. Whereas the other one is we take the average of the piano tuner numbers that are in our sample, and we multiply by 2, which we think will work because of this math. Cool. So yeah, in this case, pretend that it lists it out here. The population is 1, 2, 3, and 4, so there are 4 piano tuners, right? And we randomly sample this to get the sample. We find piano tuner with the label 1, and piano tuner with the label 3. So here we have a list, my sample with 1 and 3, and it just wants you to do what I just tested up here, which is first the example mean-based estimate is you call mean-based, should we call it? Mean-based estimator. So mean-based estimator. And we call it on my sample right here, right? So my sample, whereas example max-based estimate, we call max-based estimator on the sample, right? And then it has these two print statements, so we'll see what it estimates. So from a population 1, 2, 3, 4, we get one piano tuner number 1 and piano tuner number 3 in our sample. And which one does best? In this case, the mean estimator does better than the max, right? Because the biggest thing in our sample was 3, but actually that's just because we didn't get the highest numbered person, who's 4, in our sample. Whereas like the mean-based estimate doesn't depend on like, oh, hopefully the highest person that you sample is close to the highest person in the population. Actually, it just uses the information, like all the information, right? Because it averages it. It takes all the information you have, finds the average of it, multiplies it by 2, right? So in this case, the average of 1 and 3 is 2. You multiply by 2 and you get 4, which turns out to actually be correct. It's the population n, right? So in this case, mean-based estimate does better. Cool. But now let's think about like, okay, so will it always be the case for any sample of piano tuners that the mean-based estimate does better, right? If it's yes, set your answer to just be none. But otherwise, if you think, oh no, actually there's some cases where the mean-based estimate will do better and some cases where the max-based estimate will do better, then you can say by setting Q1F answer equal to the actual sample, right? So in this case, I'm going to say, like we can find, so let's take this population right here, right? 1, 2, 3, 4. So we saw that with this particular sample where we sample from that population and we get person number 1 and person number 3, the mean-based estimator does better. But what if we took a sample of size? Well, the stupid case is like, what if we took a sample of size 1 and we just got 1, right? Or yeah. Let me like back up, because when I was doing this, the way I thought about it was like the max-based estimator will do perfect, right? As long as you get a lot of people that are close to the actual population max, whereas the average actually depends on like, hopefully you get something that's like evenly distributed, so it's like close to, you know, what the numbers would look like if you actually had 1, 2, 3, 4, 5, 6, 7 up to n. And you can just think about like, so what samples would do well? What samples would like be most conducive to this estimator getting the population parameter? Well, the max base estimator will do best anytime you have the actual highest number, right? So let's say we have like 1 and 4, right? So instead of 1 and 3, like up there, we have 1 and 4, right? So we sample 2 people, but we actually get the lowest person and we get the highest person, right? So now let's compute mean-based estimator and max-based. So mean-based estimator of Q1F answer and max-based estimator of Q1F answer. And I have to print these. Forgot. So print the result of computing the mean-based estimator and print the result of computing the max-based estimator, right? And it turns out, even though the mean-based estimator did better up here, the max-based estimator does better here, right? It actually guesses the correct one, but that's actually only because like it's kind of cheating. It's because we actually happened to be lucky and we actually managed to, the person who was highest in the entire population, we also got in our sample, right? So in most cases, the mean-based estimator is going to do better. But, you know, it could also like say that, so say that actually the population, oh, sorry. So like you can just put this as the answer, right? Because we see here, 4 is the population, n here, and max-based estimator guesses it perfectly here because we actually got the max person in our sample, and mean-based estimator does not get it perfectly. It's one off. But say that the n was actually like 50, right? So say that like you had piano tuners 1, 2, 3, 4, ... up to 50. Then you can imagine like if you had a sample where of 4 people where you happen to get like 1, 2, and then like 43 and then 45, you'd also get well, you'd get, so now like the mean would do way worse, right? The max would do okay because 45 is close enough to like 50, you know, which here we're assuming is the highest. But the mean-based estimator doesn't even, it's like, doesn't even come close because our sample was not like spread evenly between 1 and 50, right? We had the three very lowest people and then one person that was close to the highest, right? So it's, yeah, it's not gonna, there's different cases where you can kind of get lucky and the mean-based estimator works, or you can get lucky in a different way and the max-based estimator works. So that's kind of the point of that one. Now, all right, we move on to resampling, right? So since we lack a census, which would be an actual list of all the piano tuners in the population, in this case, New York, we go into the population. We would like to go out into the population and take another sample, but unfortunately, we just have the one sample we have already loaded. So instead, we resample from our original sample, right? So that's the case I was talking about where maybe it was like really costly to do that sample with piano tuners, or maybe New York's on COVID lockdown, and so you can't just like go around asking people if they are piano tuners, right? So in that case, we just have our one sample and we have to work with it. So we will kind of squeeze as much information as we can out of it by resampling from it. So treating it kind of like what's happening here, if you can't tell, is like we're kind of taking our original sample, treating it like a temporarily like it's the population and taking subsamples from that, right? So it's like sample of the sample, and then we treat the sample of the sample as if the original sample was the population. Because we can use a lot of the statistical techniques we learned about inferring from sample to population to infer, you know, things about the sample. So great. So in helper functions, we have a function called sample with replacement, right? So what that means is like, we're going to take our original sample, right? up here we have our observed sample of 17 piano tuners and their labels. And we are going to resample from that by sampling 17 times, but like we sample with replacement, meaning we look in our data and we sample a piano tuner, but then we put that piano tuner back in the list, right? So we might pull that piano tuner out again, right? So the point is sample with replacement means you can pull the same thing out more than once. And so, yeah, what we're doing here is we're taking the label column, which is the only column, but pandas is annoying and it forces you to say the variable name, even though there's only one. We're taking observations label and we are sampling this many things from it, but with replacement, right? So if you think about it, if we sampled without replacement, the biggest sample we could possibly take is 17, right? Because after that, we'd run out of numbers, right? If we're sampling without replacement, you take one out and there's 16 left. Then you take another out and there's 15 left. You take another out and there's 14 left. So you can only do that 17 times. The key difference when you sample with replacement is we could generate a sample as big as we want, right? It would start to be pretty dumb because you would have a data set of 1,000 things, but it would only be like a bunch of repeated observations of 17 unique things. But the point is, like, we can do that, right? We can generate samples as big as we want with replacement. So we call sample with replacement and we store it in resample, and then we put resample as the last line in the cell so that we can see what is inside it, right? So what we see is we get an array of 17 things, and it let's see, yeah. So already we see that it has repeated. So like it pulled out one piano tuner from our original sample, and that piano tuner was number 84. And then we pulled out another, and it was 36. But we put the 84 back in the data set. In like a normal statistics class, you'd learn this as like an urn, or like a lottery, where so you have like this big tub of numbers and you pull a number out, and then you can either put the number back in so that like the same person can win twice, or you take it out so that like each winner is a different person, right? So in this case, we take out piano tuner number 84, but we put them back in. Take out piano number 36, put it back in, and that's how we can get 36 again here, right? So 36 appears twice, and that is, 84 also appears twice, right? It appears there, it appears again there, and it appears one more time there, right? So the point is, yeah, you can tell the difference. There's only one like if we did sample without replacement, it would be a pretty dumb sample. It would just be rearranging the order, but it would just have all the same elements as our original one. So now we have 4 statements about the resample, and we have to see which ones are true. So can the resample contain numbers that are not in the original sample? The answer is no, because where would they come from, right? We're just picking elements of the original sample, so there can't be a number that wasn't in our original sample. Number 2, the original sample can contain numbers that are not in the resample. So, right, this is the other way around, and that's actually true, right? Because we might just never get a number, right? Like we might just get unlucky, and a certain element of the full original sample just never gets picked, right? So maybe piano tuner number, like, I don't know, let's look up here. 57, is that in our sample? No, so there we go, yeah. 57 just happened to, even though it was in our original sample, it never got picked when we sampled with replacement. Just some other number always got picked instead of 57, or whatever it was. 57, right there, yeah. Cool. Now, but that's true, right? The original sample has numbers such as 57 that are not in the resample. They just never get picked by bad luck. Number 3, the resample has that. Oh, so sorry. Let's record down when we find one that's true. Let's record it in this true statements list, right? So number 2 is true. And number 3, the resample has either 0, 1, or more than one copy of each number from 1 to n. That is kind of a dumb statement if you think about it for long enough, but yeah, the point is basically that the resample can have 0 copies, right? Meaning it could just never pick something like 57 that we saw. It could have 1 copy where it just happens to get picked 1 time, or we're gonna have more than 1 copy, right? Like 84 here, it happens to get picked 4 times in a sample of 17, right? So 3 is true. And number 4, the original sample has exactly 1 copy of each number from 1 to n. Well, no, that's the whole point, right? If the original sample had a copy of each number from 1 to n, we wouldn't need to estimate anything, right? Because we would just look at the biggest thing, and that would be n. But no, we don't have all the numbers from 1 to n in our sample, right? That's the problem. Cool. So true statements is 2 and 3. Great. Now, finally, instead of multiple choice stuff, we're going to be writing some code. So let's write a function to generate different resamples, right? So all we're doing is taking what we did up here once and just doing it a bunch of times, right? So we can get a bunch of like fake samples of the sample, right? So this is what I mean when I say like we're squeezing as much information as possible from the sample. Is like now we kind of pretend using methods of statistics that instead of just like 1 sample, we have many samples. We just have to keep in mind that at the end of the day, we really do only have 1 sample. We're just using it kind of like, yeah, I can't think of a better analogy than like squeezing it to get as much information as we can out of it. So yeah, basically what's happening in this code is it's taking out the column that we want, right? Label in our observations data frame. Sample size is number of observations. So that's what we did up here, right? Number of observations, it was 17, remember? So we are resampling so that we get new like resampled samples that are the same size as our original sample, right? So 17. And now in this cell, we'll use the mean-based estimator, right? But in the next part, we'll use the max-based estimator. But the point is, this is like very trippy here. This, I think, might have tripped a lot of people up last class. I mean, last lab is that like, even though statistic is a variable, right? It can actually hold a function, right? So in this case, statistic is a variable, but instead of like an int or a list, it's actually like a whole function, right? It's a block of code. So in this case, we're saying statistic is a variable and it holds mean-based estimator, which is this function that we wrote up here, right? This function right here. So now statistic is holding that function. And now what that means is we can like give this function, we can give this code right here to our sample with replacement. Yeah, to our sample with replacement, or we could just use it in our for loop, however we want. And yeah, we're gonna do 1,000 resamples. So we'll get 1,000 data sets with 17 elements each. Cool. So yeah, this is like the standard for loop code that you've seen. Hopefully you're getting a little bit used to it, which is that you have an estimates list that starts out as empty, and then do a for loop that goes, you look kind of when you're reading a for loop, you kind of want to start at the right side, right? So you want to see what it's looping through. So in this case, it's looping through range, number of replications, right? So remember range, if you only give it one thing, starts from 0. So in this case, we are looping from 0 up to number of replications, which is 1,000, right? So we have 0. So the first time through, this replication, right, our variable inside of each for loop, replication will be 0 the first time, then 1 the second time, then 2 the third time, and so on. So, right, so far that's the same as the for loops we've seen in prior labs and homework 3, 4. But now, so new data, right, is we sample with replacement. So this, right, is just we're going inside the for loop and we're just doing sample with replacement. We're just doing this thing we did up here, right? We're getting a new resample where some things can appear more than once and some things can appear none. And what we're doing is now, this is a little confusing because 2 things are lumped together here, but the point is we have new data, which is now, it's a list of 17 elements, but it's not the same as our original sample, right? It's a resample from our original sample. And now what it's doing is it's taking our statistic variable up here, and like this is the nice thing about being able to store a function into a variable is whatever is in statistic, we don't care. We just say called whatever function that is, passing in new data as the parameter, right? So it takes this new data set that was generated and it runs our statistic function on it, right? Whatever we set up here. So in this case, since statistic is assigned to be mean-based estimator, this will call mean-based estimator on new data, right? This is just here to show you that, like, you know, you could have 50 test statistic functions and it would get really tiresome to like write code to call all 50 of them, right? So what you could do is you could just have like all the functions, you know, in a for loop and call them different statistic functions one by one. But I'm just saying, like, it is very useful that in Python, you can put functions into variables. So what we do is we compute the statistic on new data and we append it to estimates, right? So the list starts out empty the first time, right? It generates a new data set, computes the statistic, runs the statistic function on the new data set, and then appends whatever the result is, whatever the, in this case, mean-based estimate is, into estimates. So the first time through, now there will be a single element added to estimates, which will be the mean-based estimate of our randomly generated resample. And then it'll run a second time. It'll generate a new resample, right? It'll do another process of pulling out elements from our original sample 17 times with replacement. Then it'll compute the test statistic, and then it will put the test statistic from the second resample into our estimates, right? So by the end, we'll have 1,000 things in estimates, and each one will be like, okay, we generated a data set here, we ran our statistic function on it, and we added it. We did estimates.append, so we added it to the end of estimates, right? Cool. And so this line just shows the first 10 estimates, so we can check that it worked, right? And so cool. We see that, like, okay, the first time it generated a resample, a sample with replacement, and it got 137.529, right? As the mean-based estimate, right? So 2 times the mean of our sample was 137.5. Second time, we generate a different resample, right? Things that were included in the last one might be excluded in this one. Things that were excluded from the last one might be in this one, and that's why you'll get a different number, right? So here, 2 times the mean is lower. Here, 2 times the mean is even lower. Back to 122, right? But you get it that each one of these is the result of doing a full resample of 17 elements, and then computing the mean and then multiplying by 2, right? And we have 1,000 of those. This just printed the first 10 because of this :10 thing here. Cool. And so now we want you to generalize one more time, because here, right, we just wrote like a code cell. So if we wanted to do this a bunch of times, generate 1,000 estimates, if we want to do that a bunch of times, we'd have to like sit here pressing like shift enter, shift enter, shift enter a bunch of times. So instead, we'll make a function that does that, right? Because then we can just call that function however many times we want, like in a for loop, for example. So in this case, make a bootstraps estimate function, and it takes in 4 things, right? It takes in the data, so that's the column of the data set. It takes in sample size, so the number of things that you want in each resample, right? We've been using 17 so far just because that's the size of our original sample. So when we resample things, like, it's just nice that the resampled list of piano tuning IDs is the same length as our original sample, so that they're comparable, right? Like when we, you know, take the averages and stuff, we can compare them with the average of the original one. Statistic is the function. So again, we can drop in whichever function we want. We can put in mean-based estimator if we want to do this bootstrapping using the mean-based estimator, or we can put in max-based estimator if we want, right? So one of the nice things about having a function instead of just a code cell. Cool. And then number of replications, right? Which is just, we do the resampling 1,000 times. Cool. And so it's actually the exact same, like we could copy the code from up here, right? Because we have the same, once we're inside that function, right? Once we've said def bootstrap estimates, and we've said what parameters it's going to take, if you look at it, like the code inside of this function is just going to be the exact same as the code that was in this code cell, right? So I'm just going to copy the code from that and paste it. So, well, okay, I won't do that just because it's even easier. We only really have to write one line, right? So we are inside the for loop, right? It created an empty estimates list, and it is doing number of replications. So this loop is going to run 1,000 times because we're going to give 1,000 as number of replications when we call this function, right? And so what do? We create a new data set, right? We say new data equals, we want to sample with replacement, right? And remember from up here that sample with replacement, you just give it a sample size, right? The number of things, and you give it the data set it should sample from, right? So we want a sample of size, sample size, right? That's our parameter right here. And we want it to sample from data, right? Which is the first parameter here. Cool, so now we've generated our new data set for that inside of the for loop. So for that one iteration of the loop. And now we want to compute the estimate from the new data. So say new estimate equals, and remember now we don't specifically call like max-based estimator or mean-based estimator by name. We call whatever statistic is, right? So we just say, all right, they're giving a statistic, which is going to be some function. So I'm going to be able to call it and give it new data, right? And so now we can get our new estimate from that, whatever a statistic is. It's a variable. And finally, now that we have our estimate, we want to add it into our estimates list, right? So estimates.append new estimate. Because if we didn't do that, it would like compute new data and it would compute new estimate, and then it would just throw it out. Because at the end of the for loop, it deletes all the variables that were created in that in that iteration of the for loop, right? And so our function now, it creates an empty estimates list. It does the exact same thing we did above, right? It fills the estimates array with 1,000 estimates of n, whether they're by the mean or by the max method. We can set that by sending in different values for statistic, and then it just returns that estimates list, right? So great. So now I would just use it here, but we're going to use it in the next question anyway. So now we're going to use that to generate estimates from 1,000 resamples, right? So we have data, which is the same thing we've been using all along. It's the data frame label column. Then we have number of observations, 17. Statistic, which is we want to use the mean-based estimator here. And number of replications is we want to resample 1,000 times and get 1,000 estimates from those resamples. So now, since we have this nice function that we made, we can just call that, right? So bootstrap mean-based estimates is bootstrap estimates, right? We call that bootstrap estimates, and it takes 4 parameters. So data, we've got that defined right here, right? Data. It takes a sample size parameter, right? Which we have here, sample size. It takes a statistic parameter, right? Which here we have has been set equal to the mean-based estimator. So, or to be fair, we could just write mean-based estimator, whichever one you want. And then it takes a number of replications argument. In this case, we've set that to 1,000, so number of replications. Cool. And just to make it look a little more clear, I'm going to do that, right? When you have a comma separated list of arguments, you can put a comma and have the next one come on the next line, and Python will be smart enough to figure it out. So cool, we have bootstrap mean-based estimates, which is using our function from above to generate 1,000 estimates, right? Using the mean-based estimator. So just for like sanity, to make sure that it worked, I'm gonna print out the first 10 elements at the end. Bootstrap mean-based estimates. 10. Cool. So it's similar to before, right? We get a list of 10 estimates. I mean, we actually get a list of 1,000 estimates, but the 10 estimates we can go through like we did before. This is saying that when the first resampling that we did, we took the average of all the numbers multiplied them by 2, and we got 143.4. We did that again, we got 117.176, so on and so on. And we can plot those, right? So we can, this is like a histogram of, let me make this smaller. Yeah, so this is a histogram showing us essentially like what the mean-based estimator, the distribution of values that the mean-based estimator gives when we resample, right? So it's kind of nice because before, if you asked like, oh, what does the mean-based estimator give? We would just get a number, right? We would run the mean-based estimator on our sample, and we would just be like, all right, it's like 130 or something, right? We would just get a number. Whereas now we're using resampling to squeeze out more information, because now we actually get a distribution, right? Saying like, oh, if like sometimes something was included more than once and other times that thing was excluded and blah, 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 like what would different kind of like permutations or modifications of the original sample, what test estimate would that give us, right? What mean-based estimate would that give us? And that shows that it's like robust, meaning like if we always got like a really similar mean-based estimate, even if we like threw out half the data or like only picked every other thing in the data, or took like the first quartile and the highest quartile, right? If we like chop the data in all these different ways and we still get, most of the time we get 120 for the mean, the estimate of the mean, that tells us something, right? That tells us kind of like, oh, it's like more information than just the mean-based estimator run on the sample, right? It's saying that even when we like mess with our sample, when we take people out of it, or we include people in it more than once, we're still getting 120 each time, right? So it tells us it's more information about it. It also tells us like how spread out they are, right? If we like got a hugely spread out thing, like say it was spread from like 5 to like 1 million, that wouldn't be very good, right? That would be saying like, well, our sample's kind of weird because like if you take out like 2 of the numbers, suddenly the mean base estimate jumps up to like 1 million, right? So what we would want is like, we want there to be a value that it gets like a single peak, right? Meaning like we want it to have a single mean value, and we want it to not be that spread out, right? Because that tells us like how confident can we be in saying 120 is the actual n, right? Cool. So now it's nice because we've written our function, so now we can repeat 2C using the max base estimate, right? And so what we do is, whereas up here we had set, I'll zoom back in. Whereas up here we had set statistic equal to the mean based estimator, the only thing we change now for question 2D is we change statistic equals max based estimator, right? And then we call our bootstrap estimates function again, right? It takes data, it takes sample size, it takes statistic, which this time we've set to be max based estimator. So I'll just write statistic, and it takes number of replications in that order. And I will break that to make it look nicer. Cool. And I can uncomment this and it will print out the first 10 things, right? So when we do our bootstrap, but we do it with the max-based estimator instead of the mean-based estimator, right? We get kind of a weirder looking thing, right? We get a thing where like most of the values that we see, at least in the first 10, are 135, right? Which makes sense because if we go back up and we look at what's the max in this entire data set, right? We saw that it was 135. So it makes sense, right? It's just saying like anytime, basically like anytime we take a resample and that resample includes 135, that's going to be the max base estimate, right? Because it's going to 135, if it's included in the resample, is guaranteed to be the greatest number. Whereas like this one, right, it's 108 because I guess like in this resample, 135 did not make it in, right? 135 was never picked. So instead on resample number like 1, 2, 3, 4, 5, 6, on the 7th resample, 135 was not included in the resample. So actually the biggest thing in it was 108, so it guessed 108, right? And in this one, 83 was the biggest thing in it, so it guessed 83. So we can plot this like we did before, but we'll get a weird thing, right? Which is that like most of the time 135 was the estimate. Sometimes 110 was the estimate, sometimes 80 was the estimate, right? about like, what is this? Like 12% of the time. Well, I don't know. I don't have it set to percents. So the point is just that like, instead of getting a nice distribution, the max base estimate just gives us like, all right, most of the time I got 135 because most of the time 135 was included in the resample, but when it wasn't, I sometimes got 110, and I even less of the time got 80 or 108, and less of the time got 83. Cool. So can the max base statistic generate an estimate greater than 135? The answer is no, right? It's really, it relates to the thing that we saw up above, which is like, oh, can the resample include things that the original sample didn't include? The answer is no, right? So in this case, max base statistic cannot generate an estimate greater than 135 because 135 is already the greatest thing in our sample, greatest number in our sample. So B, no. All right, computing confidence intervals. So now say we scour Yelp to determine, so we type in piano tuner in Yelp, and we find that N is 150, right? So say we find the truth, right? That actually there's 150 piano tuners in New York City, and our sample is a sample from that population, right? The true population is people with label 1, 2, 3, 4, up to, 148, 149, and 150. But we have this sample where it's, let's find the min too. So we can do, we got that the max is 135, but we can also do observations label dot min. And that's 21, right? So in our sample, the lowest person we got, the lowest numbered person we got was 21, and the highest numbered person we got was 135, right? But in reality, in the population, the lowest is 1, and the highest is 150, right? And so for this last one, we're going to do confidence intervals, and we're going to see, like, do these confidence intervals actually, like, help us, because it's like, now that we know the population, do the things that we computed about our sample in question 2, do they actually help us infer things about the population? So yeah, we want to compute a 90% confidence interval, right? We want to compute an interval that covers 90% of the mean-based bootstrap estimates, meaning, like, so that's equivalent to saying, like, we want to take all the bootstrap-based estimates, and we want to find the 5th percentile, and we want to find the 95th percentile, right? And that's literally saying that, like, 90% of all of our bootstrapped estimates were between these two values, right? And that helps us say, like, okay, if our bootstrap estimates are doing well, right? So if like our sample is actually helpful in us estimating things about the population, then we should be able to take these bootstrap estimates, right? Compute a confidence interval based on them and say, like, oh, we're like pretty confident that the true mean is in here somewhere, right? So we have another helper function called calculate percentile, which takes 2 inputs. It just takes in an array of numbers that you want to compute the percentiles of, and then the percentile that you want to compute, right? So between 0 and 100 inclusive. So in this case, it wants you to say left end, right? It wants left end to be the 5th percentile of the distribution. So we say calculate percentile, and it takes 2 inputs, an array of numbers. In this case, the array of numbers is, of the estimates. Yeah, sorry. So we have our list of estimates. This is our list of estimates from the mean-based estimator, but the question says, well, we want to use the mean-based estimators, right? So sorry, these are the max-based estimates. We want to go back up more and find our, what did we call our mean-based estimates? Our list of mean-based estimates is bootstrap mean-based estimates. So that's what I'll use down here. Say calculate percentile of bootstrap mean-based estimates. And I want the left end is the 5th percentile. It says up here, right? In a 90% confidence interval, the left end is the 5th percentile and the right end is the 95th percentile. Actually, where is it? Yeah, I made this, or not, I didn't make it, but I found this image that helps us see that, right? If we cut it off so that we cut off the lowest 5% of the data down here, and we cut off the highest 5% of the data, what will be left over, right, is a 90% confidence interval, because 90% of the estimates live in between these two cutoffs, right? So that's what we're doing here. Is we're taking bootstrap mean-based estimates and we are finding the left end, which is the 5th percentile, right? So we just give 5 to our calculate percentile helper function. And here, right end, we do same thing, bootstrap mean-based estimates. This time we find the 95th percentile, right? And that'll give us our 2 cutoffs, meaning that any bootstrap estimate that we got between these 2 values, that's in our 90% confidence interval, right? And so we're just going to print them to see. Cool. So what this is saying, like for interpretation purposes, is that 95% of the data, right, was above 98.235. And then, since this is the 95th percentile, 95% of the data was less than 146.588, right? And so what that's saying, right, is like our mean-based estimate statistics histogram up here. Most of the estimates that we computed using the mean-based estimator fall between like 98.235. So that's like around here, right? And 146.588. So that's like here, right? And so, yeah, we're literally just, hopefully this picture, oops, sorry. Hopefully this picture makes it make a little sense of what we're doing, right? We're just cutting off 5% on the left and 5% on the right so that, you know, we say 90% of the estimates were between these 2 values. It makes sense because those are the bars that are the biggest. Okay, cool. And so now this code is given to you. You don't have to write anything, but it just does that, right? It makes this histogram. I'm gonna zoom out a little bit. Makes the histogram and it shows you like the yellow here is, that's the 90% confidence interval, right? But one issue is that the red dot on the histogram is the value of n. So we put like the actual value, right, 150, and we see that it's there. So actually like the sample is unlucky in the sense that if you resample from it a bunch of times, even 90% of the time, we're not going to get the true value, right? 90% of the time, we get something between 98 and 146, but actually the true value is 150. So yeah, we are in the unlucky 10%, right? Where it's like, oh, 10%, we're 90% confident that, in a sense, that our mean is in here, but we're 10%, like there's a 10% chance that it's not. By the way, that's not like the statistically correct way of phrasing it, but as I'm using it as shorthand, that basically we got unlucky. Our sample is not big enough or not representative enough of the population to make our confidence interval help us, right? Our confidence interval didn't help us. The true value from the population was not even in our 90% confidence interval. Cool. And so now we're going back to the case where we don't know the actual truth n, right? But based on the bootstrap of one sample, we generated this 5th percentile to 95th percentile confidence interval, and it didn't contain our true n, right? But if we had another random sample and we did a bootstrap on that sample to generate a 1st percentile to 99th percentile confidence interval, right? So now that's 98% of the data, right? Because we're only cutting off the bottom and the top 1%. So it's a 98% confidence interval. So would that confidence interval on average be more or less likely to contain n? And just like by, you know, common sense, it's like, well, okay, it's a wider interval, so it's going to be more likely to contain our true thing, right? So yeah, we get this less and less and less precise band of values, but we can be more and more and more confident that the true n is inside of that, right? Meaning like if someone, like if your boss comes to you and they're like, I need, you know, 100% or I need 99.9% confidence that like the estimates that you give me are going to be the true estimate. And so you're like, okay, well, if you want to be that confident, I'm going to say it's between 1 and 1,000,000, right? Then you can be really confident that it's in there, but it doesn't help you much, right? Whereas if you start to narrow that band, your confidence level has to go down, right? Maybe it's like you're 99.9% confident that it's between 1 and 1,000,000, but between like, you know, 1,000 and 5,000, if you want to get it to that narrow of a range, then your confidence level has to go down. So the point here is that if you increase the confidence from 90%, which it was here, right? This yellow band represents 90% confidence interval. We increase it to 98%, we're more, it's like, and we widen this band, it's more likely to contain N. So the answer is A. I'll make that bigger. And now finally, say instead of one sample of size 17 from the population, we have 100 samples, right? And we do the same thing we did above. We applied bootstrap resampling with 1,000 replications for each of those 17 samples, right? So the point is we just do like the whole Jupyter notebook we just did, but we do it 100 different times, right? Because instead of one sample like we had at the beginning of this notebook, now we have 100 samples, right? And we compute a between 5th percentile and 95th percentile, that's a 90% confidence interval, right? Because of, remember this picture, right? So among the 100 confidence intervals that we get, right, from our 100 samples of size 17, now how many should we expect to contain N? That is when I was talking about like, oh, like we're pretty sure it's in this band. I was talking about that above. That is like the imprecise way to talk about what a confidence interval. The precise way to talk about what a confidence interval is, like from a statistically principled, like there's the correct statistical way to say what a confidence interval is exactly this question, which is like, if you do the procedure 100 times, how many out of those 100 times would we expect it to contain N, right? The 90% confidence interval, like the definition of the 90% confidence interval is an interval such that if we construct that interval 100 times, right, in the same way, so we just take 100 samples and for each sample we construct that interval, 90% of the time, if it's a 90% confidence interval, 90% of those 100 intervals that we construct should contain N, right? So in this case, yeah, we're computing a 90% confidence interval 100 times. The correct way to interpret a confidence interval statistically is to say the 90% confidence interval is the band of values such that if I compute 100 of them in the same way, I expect 90 of those 100 to actually contain the true value that I want, right? So in this case, we have 100 confidence intervals. How many should we expect to contain N, right? It's a 90% confidence interval. By that definition, we would expect 90% to contain N. So the answer is D. Cool, now you're finished. There's like, this is the hardest unit by far, I think. And it's also like, you shouldn't, even though it's the hardest, you shouldn't worry, you should worry about it the least, because if you think about it on the project, right, which is a fairly big part of your grade, there's literally one of the 16 questions is about confidence intervals, and it's not even about doing any of this bootstrap stuff. It's literally about like your regression program, or whatever you use to run a regression using your data set, it will give you a confidence interval, and the question is just asking you to interpret it, right? So the interpretation is just like, if I collected 100 samples, right, and I ran this regression 100 times, if it's a 90% confidence interval, that means 90% of the time, this interval should contain, sorry, 90% of those intervals should contain the true value. So I'm going to do another video on regression just because like we need to get to that. So please like worry about this 1/4 as much as you worry about regression, right? Because one question on confidence intervals, but 4 questions on regression. So